Good afternoon, students. Welcome to the lecture of Operation Research. In the last lecture, we have studied a method called as the Lagrangian method of multipliers, which is used to solve a non-linear programming problem. Instead of to solve, I can say it will provide us the necessary conditions for finding the optimum of the given objective functions, right? And this method was mainly or rather used for the nonlinear programming problem, where quadratic programming problem is the special case of nonlinear programming problem. Nonlinear means there are no restrictions for the linearity on objective function as well as the constraint. But in quadratic programming problem, we were giving the restriction for our objective function to be quadratic and constraints to be linear. Now this method is going to provide us the necessary conditions which will help us to find out the optimum of the objective function. Therefore, the method is used only when the constraints are in the form of equations. Constraints are equation. Therefore, the method we have studied first for the function of two variables. Rather, it's a differentiable function subject to the equality constraint in two variable where the function is also differentiable. Therefore, if we assume the objective function assumes the optimum at the given point x naught, y naught, and one of the partial derivatives dou g by dou x or dou g by dou y does not vanish, that is both of them do not vanish simultaneously at this point, then we can write at near this point x naught, y naught, we can write the equation g of xy equals to 0 as y equal to h of x. Then differentiating this g with respect to x, we have obtained this equation number 3. Later, for the extrema of the objective function, the first derivative of f must be equated to 0. Then finding the first derivative of x, we are replacing this y function, y variable with h of x. This is what the second equation we have. Now, as we have assumed one of the partial derivative is non-zero, let me start with an assumption dou g by dou y is not equal to 0. If we assume dou g by dou y not equals to 0 at the point x naught, y naught, then define a parameter lambda which is actually called as a Lagrange's multiplier. This is actually called as Lagrange's multiplier. And the value of this Lagrange's multiplier lambda is obtained by dou f by dou y minus dou g by lambda times dou g by dou y is equals to 0, which in turn gives us the value of lambda as dou f by dou y upon dou g by dou y. Then we will do an algebraic operation. We will multiply 3 by lambda and subtract from 4. This is what the equation we will obtain, right? But this equation we have already kept to be 0. No? We have found the value of lambda which gives us, which is obtained by dou f by dou y minus lambda times dou g by dou y. Therefore, this putting the value of the second bracket is equal to 0, we will obtain the first bracket as well as equal to 0. Therefore, now we have in hand now two equations. First equation and second equation. First is dou f by dou y minus lambda times dou g by dou x is equals to 0. Similarly, dou f by dou y minus lambda times dou g by dou y equals to 0, moved out at the point x naught, y naught. So looking at this, Lagrangian has set up the new function called as the Lagrangian function, which is defined to be L of x y lambda. Lambda was involved in the equation, therefore Lagrangian function is defined to be f of xy minus lambda g of xy. Therefore, looking at both the equations, may I say first equation is obtained by finding dou L by dou x equal to 0. Second equation is obtained by putting dou L by dou y is equal to 0. And if I differentiate with respect to the Lagrange's multiplier, that is the parameter lambda, it gives us the original constant equation. So there are three equations in our hand, where the three equations provides us the conditions for the optimization of this Lagrangian function L. Therefore, one can say these three conditions are the conditions for the optimization of unconstrained optimum L, and which are actually giving us the conditions for the optimization of the original objective function, because L is constructed with the help of objective function and the constraint. Therefore, the necessary conditions for the unconstrained optimum of L are also the necessary conditions for the original objective function, that is optimum of f of xy under g of xy. Therefore, this is the Lagrange's method of multiplier. One can extend the same method to the function of n variables subject to m constraint. The Lagrangian will be constructed in this case as giving one Lagrange's multiplier to each constant equality. Because this is my Lagrangian equation, right? Therefore, each constant equality multiplied by lambda will be subtracted from the original objective function. Therefore, here we have actually n original variables, m Lagrange's multiplier. Therefore, this function, this Lagrangian function will be a function of in all m plus n variables. Now, the necessary conditions tells us differentiate this L with respect to original variables as well as with respect to Lagrange's multiplier. If we differentiate with respect to Lagrange's multiplier, it will give us the constant equation, and differentiating with respect to original variables gives us this equation. Therefore, we have in all m plus n equations with us, right? M plus n. And these are giving us the necessary conditions for the optimization of the given programming problem. And these necessary conditions become sufficient for the maximum objective function if the nature of objective function is concave, and for minimum objective function it becomes sufficient if the objective function is convex. Now, in today's lecture, we are going to construct, or rather we are going to use this Lagrange's method of multipliers for forming the necessary conditions for the quadratic programming problem. And firstly, these conditions were derived by the pair of mathematicians Kuhn Tucker. That's why the heading will be Kuhn Tucker conditions. So in today's lecture, we are going to construct the necessary conditions for the quadratic programming problem, which are called as Kuhn Tucker conditions. To construct Kuhn Tucker conditions. Kuhn Tucker conditions for quadratic programming problem. Right? Now let me just give a brief introduction about the two mathematicians Kuhn Tucker. Right? The full name of the mathematician Kuhn is Harold W. Kuhn. The life tenure is 29 July 1925 to 2 July 2014. And he was American mathematician. And the work is mainly for game theory and operation research. Second mathematician, Albert W. Tucker. The life tenure is 8 November 1905 to 25 January 1995, and he was a Canadian mathematician. Okay, and the pair has used Lagrange's method in order to construct the conditions for quadratic programming problem, and that's why those conditions are called as Kuhn Tucker conditions. Okay. Now let us come to what are the conditions actually. Now we are going to use Lagrange's method. Therefore, what is our first job? To construct the Lagrangian function, right? By considering all the constants in the form of equations, then differentiate this Lagrangian function with respect to all the variables involved, equate the derivatives to 0. Start up. Before constructing, let me write the quadratic programming problem once again. Therefore, let me write QPP. What is the QPP? Maximize z is equal to f of x, and which is actually summation j equals to 1 to n cj xj plus half times double summation j equals to 1 to n k equals to 1 to n cjk xj xk cjk xj xk, and which is subject to the constraints. Subject to the constraints. What are the constraints? Summation j equals to 1 to n aij xj less than or equals to bi, and xj greater equal by 0. Xj is greater equal by 0. What are the values of the parameters? I running from 1 to m and j running from 1 to n. M constraints and n equations. Correct, no? M equations and yes. Okay. For I equals to 1 to m, j equals to 1 to n. Where what for the Cjk coefficients? Cjk equals to Ckj, no? Why it is so? Because we were considering Q to be a symmetric matrix. Here let me write a reason. Since Q is symmetric matrix. Actually, we have seen the matrix form of this quadratic matrix representation of this quadratic form. Since Q is a symmetric matrix. And what for the right hand side constraints? Sorry, right hand side constant, Vi's are non-negative. Is that fine? This is my quadratic programming problem. Now, in order to use this Lagrangian method, first we will try to convert all inequality constraints to equation. Now, this is the first method ever in which we were considering this non-negative constraints, and we were also considering this to be constraints we were converting into equation. Therefore, how many constraints we were now going to convert to equations? These are in all m constraints and these are in all n restrictions. Now we will convert each and every constraint to be equations. For converting the first type of constraints, we were going to use slack variables. Okay. Now, if I use a slack variable, suppose there are in all n variables, no? Generally, we were using xn plus 1, xn plus 2 as a notation, that is xn plus j as notation for the slack variable. But if I add xn plus j, again that xn plus j must be non-negative. Now we were converting those constraints to be equations again. Therefore, here in this method, instead of adding the variable in the form of xn plus j as a slack variable, we were adding a squared variable. Okay, we were adding a squared variable so that there is no need to impose the non-negativity restriction on that corresponding variable. Therefore, here what I am writing, adding slack variable qi square. Qi square are the slack variables we were adding to this one, and this is a greater equal constraint. How can I convert it to less equal? Minus xj less than or equals to 0. Correct now? Therefore, if once it becomes less equal, we can add a slack variable. Let me write the slack variable to be rj square to constraints. Okay, is the point clear to everyone why we are adding squared variables?
Yes, ma'am.
If we do not add square variable, we have to impose a non-negativity restriction on those added variables as well. But here we were converting these non-negativity restrictions as equations, right? So we will add the squared variable. As these are the square variable, whatever the values of qi and rj, their squares are always the non-negative value. Therefore, let me write summation j equals to 1 to n Aij xj plus qi square equals to bi, right? No doubt, for I equals to 1 to m. And for the second one, actually we were converting xj greater equal by 0. We were writing minus xj less than or equals to 0. Now let me add the square variable. So minus xj plus rj square is equals to 0. For j equals to 1 to n. So this was the first method we were seeing in which we were converting the non-negativity restriction to equations. Till now we have not done this now, correct? Okay. Now it's a time to construct the Lagrangian function. Now as we have seen or as we have discussed already, we were going to use one Lagrange's parameter for one constant. Therefore here we have in all m plus n constraints. Therefore for original constraints, let me use the Lagrange's multiplier as lambda I, and for these constraints, let me use the Lagrange's multiplier, say mu j. Therefore, how many Lagrange's multipliers we were using in all? M plus n. Clear? Let me construct the Lagrangian function. We shall now construct Lagrange's or Lagrangian function. Okay, now let me write the Lagrangian function in terms of vectors. Lagrangian, let x be the vector corresponding to original variables. Let q be the vector corresponding to all the slack variables. How many slack variables we were adding? Q1, Q2 to Q1. And while adding, we are adding their square forms, right? Then for second, we have used R vector. What is R? R1, R2 to Rn. And then we were adding lambda Lagrange's multiplier for the original constraints, mu Lagrange's multipliers for the non-negativity restrictions. Therefore, let us just think of what is the count of all the variables. What is the count for x? How many x variables we have? X vector. How many variables in x vector we have? N. Right? No? Am I audible clearly?
Yes, ma'am.
How many original we have? Original variables. N. Correct, na? How many q we were using? Q1 square, Q2 square. How many such q? There are m constant. No. For every constant there is one q. Therefore there are m. Correct, na? I don't know why you are not responding me today.
मॅम ते कळत नाहीये कसं आलं एक्सचं आता एन काउंट कसं आलं ते
किती original variables आहेत असं विचारलं. How many original variables we have above x? How many variables x we have? You just look at this summation. Summation j
Yes,
we have
yes.
taken from 1 to n. Na?
N,
So what
N
is my
variables.
vector x? Vector x is x1 to xn, original variables, right? No? And what for the constraints? How many constraints we have? M constraints we have, right? To every m constraint, we are adding one slack vector, one slack variable, sorry. Okay. And also we were converting the non-negativity restrictions to equations in this method. Therefore, how many non-negativity restrictions we have? N non-negativity restrictions. Therefore, writing this xj greater or equal by 0 in terms of less equal, it actually becomes minus xj less than or equal to 0. Therefore, we were adding the slack variable qi square and rj square. Right? For how many q variables we were using? Q1, Q2 to Qm. Right? Now? How many r variables we were using?
N.
N. Yes,
N.
it is N. R1, R2 to Rn. And while adding them in the constraints, we are adding in terms of their square forms. And the reason behind adding in terms of square forms is we want the value to be non-negative. Correct, no? Therefore,
Yes,
now while constructing the Lagrange's multiplier, we were multiplying the constant by the Lagrange's multiplier and subtract it from the original objective. Let me show you for that two variable case. Just recall. How we have constructed this Lagrangian? From the original objective function, we have subtracted the constraints with the multiplier lambda. Right? Therefore, whatever is the constraints you have, multiply the constraints by the Lagrange's multiplier and subtract it from the original objective function. In case of n variables, we have written this, no? What kind of form this is going to take? Let me write it here. F of x minus lambda 1 g1x, correct? Minus lambda 2 g2x, correct now? And so on up to minus lambda m gmx. Means what we were doing? We were multiplying by the Lagrange's multiplier to the constraints and we were subtracting it from the objective function. The same kind of job we were doing in this for this quadratic programming problem, right? So this is the objective function. Actually, we want to write this objective function, objective uh, constant equation in terms of equal to 0. Therefore, what I will write here, this I will write minus bi equal to 0. Is there any problem? This is equal to bi, na? So we were writing minus bi equal to 0. Therefore, there are in all m constants, m original constants, and there are in all n constants for non-negativity restriction. Now, to every constant, we were multiplying by the Lagrange's multiplier lambda I for original, and for every constant of the second type, we were using a multiplier mu j, right? Therefore, what will be my original? What will be my Lagrange's Lagrangian function? F of x minus what minus? Okay, let me write my constant. My constant equation is summation j equals to 1 to n aij xj plus qy square minus bi. Now we were multiplying the constants by lambda I. How many such a constants we have? M constants we have, correct? Okay, this is what? Multiplying by lambda I to first type of constant, there are no m constant, subtract those from the original objective. Same we will do for the second one, right? Minus, okay, what is the constant equation? Minus xj plus rj square. What are the Lagrange's multiplier we were using? Mu j. How many such we have? J equals to 1 to n. So this is my Lagrangian function. Check if you have any difficulty in this. But actually the function is going to look like this. L equal to f of x minus, okay, f of x minus. What minus I should write? Lambda 1 into first constant. Let me write it for I equals to 1. Because this is summation ai1 xj plus q1 square minus b1 minus lambda 2. Let me put for I equals to 2. Summation ai2 xj plus q2 square minus b2. And let us continue this up to lambda m. Therefore, this is minus lambda n summation ai1 ai m xj plus qm square minus bm. Okay, and then we will do this for the remaining constant. Now let me put the value of j equals to 1. Therefore, this is minus mu1 minus x1 plus r1 square minus mu2. What is the second constant? Minus x2 plus r2 square. Continue this up to minus mu n minus xn plus rn square. This is the Lagrangian function we have written in terms of summation form. Understanding Lagrangian is important, very important. Unless you understand Lagrangian, you cannot understand the next conditions. Yes, any difficulty in the construction of Lagrangian function?
No, ma'am.
Good. Now let us discuss the count again. How many x we have original variables? N?
N. Yes, ma'am.
How many q we have added?
M.
M. How many r we have added? Rj square, na? R1, R2, R. Up to Rn we have added. So what
N.
is the count? N count. What is lambda count? One
M.
Lagrange is multiplied. Yes?
M.
Yes, it is M. Good. What is mu count? Mu vector?
N.
Yes, it is N. These many number of variables are there in your Lagrangian function. Getting me?
Yes, ma'am.
Should I go for the next point then? If the construction is clear to everyone. Okay, let me repeat the construction. From the original objective function, we were subtracting the constraints by Lagrange, multiplying with the Lagrange's multiplier. For original constraints, we have used Lagrange's multiplier notation as lambda I, and for the non-negativity restriction constraints, we have used mu j as the notation for the non-negativity for the Lagrange's multiplier. And multiplying by the multipliers, Lagrange's multiplier, we will subtract it from the original objective function. This is what the construction of a Lagrangian function. Is the point clear?
Yes, ma'am.
Now let me put the value of f of x. Here now I have not kept the value of f of x yet. What is the value of f of x? This is the value of f of x. Summation cjxk, double summation cjk xjx. Okay. Let me substitute the value. What is my function now? L x q r lambda mu. What is f of x? Summation j equals to 1 to n cj xj plus half double summation j equals to 1 to n equals to 1 to n cjk xj xk. This is original objective function minus now summation I equals to 1 to m lambda I. The original constraint is summation j equals to 1 to n aij xj plus qi square minus bi minus summation mu j minus xj plus rj square. Now we were going to obtain the necessary conditions. How the necessary conditions are obtained? Differentiating L with respect to the variables and equating this to 0. Rather partial derivative I can say. Differentiating partially with respect to all the variables and equating the partial derivatives to 0. Now let me just differentiate with respect to all the variables one by one. Now forming necessary conditions, what we were doing? Yes, differentiate L with respect to differentiate L partially with respect to differentiate L partially with respect to all variables and equate it to 0. Correct now? Now what the job we will do? We will try to differentiate with respect to original variables xj first. What is the original variable? Dou L by dou xj. Look at this. What is the derivative of first summation value? If I just elaborate the sum, this is of the type c1x1 plus c2x2 plus dot up to cn xn, and now we were differentiating with respect to arbitrary variable xj. So what will be my derivative of this first summation, first term? Yes, students?
CJ.
Yes, it is Cj. Good. Okay. Now we were going to differentiate this double summation. Can anyone tell me what is the double differentiation of this double summation with respect to xj?
summation k from 1 to n cj xj cj xk.
Pjk, Pjk, xk. Is it summation only or whether it is twice the summation?
डेरिव्हेटिव्ह मध्ये ते एकच येणार मॅम.
Okay, let me show you now. I'll just take another color pen and I will explain you the derivatives first. First term is summation Cj xj, na? J is equals to 1 to n. What is its partial derivative with respect to xj? If I differentiate, what will happen? Actually, the term is of the form c1x1 plus c2x2 plus somewhere jth term I will write and continue this up to cn xn. Therefore, if I differentiate with respect to xj partially, what is the value we were going to get? We were going to get cj only, right?
Yes ma'am.
Now, let me show you with the double summation. Double summation. If I take for 1 to n, it will be very lengthy. Just to explain, I will take summation j equals to 1 to 2. Summation k equals to 1 to 2 cjk xj xk. Okay. Let me try to understand what the term is going to give. First, let me run up the summation over k. And let us check how many terms we have. If I run up the summation over k from 1 to 2, what are the terms? Is it cj1 xj x1 added with cj2 xj x2? Fine? Correct, no?
Yes ma'am.
Now, actually, how many terms should be there in all in this double summation? How many terms will be there in all? Both the values of the parameters are from 1 to 2, 1 to 2. Two values it will take. Therefore, may I say there should be 4 terms actually in this summation. Okay. Now let me run up the summation over j also. If I run up the summation over j, let me put the value of j equals to 1 first. So this is c11 x1 into x1. Then c12 x1 x2. Now let me put the value of j equals to 2. This is c21 x2 x1 added with c22 x2 x2. Correct? How many terms we have obtained in this double summation now? 4 terms. Correct, no?
Yes ma'am.
Now, as per the assumption, C12 and C21 are same. So let me just rewrite as this first term is C11 x1 square. And let me write 2 times C12 x1 x2. Is it fine? 2 times C12 x1 x2 because these two are equal. And added with C22 into x2 square. What the reason here is C12 is equals to C21. For the sake of convenience, we have taken this to be a symmetric matrix. Right now, therefore double summation j equals to 1 to 2, k equals to 1 to 2, cjk xj xk gives me this value. Now let us differentiate with respect to one of the variable partially. Let me differentiate with respect to x1 partially. Okay, therefore the dou by dou x1 of this term is equal to, what is the differentiation on the right side? Is it 2c11 x1 plus, yes,
2c1 to x2.
2c1 to x2. Third term is giving you 0 value, right? Therefore, look at this term very carefully. From this, I can take 2 common very easily, and the remaining terms are c11 x1 plus c12 x2. c11 x1 plus c12 x2. Now, can I write this as summation k equals to 1 to 2 c1k xk. Why I am not writing in terms of j because I have taken partial derivative with respect to j. So let me write it in terms of k. Okay. But if I differentiate with respect to x1, this gives us 2 times summation over k 1 to 2 c1 k xk. See, here it is 2 occurring. I just want to make sure you how this 2 is occurring. Same if I take the partial derivative with respect to x2, what will happen? This is 2 times. Yes? Yes? If it
C2K
is,
XK.
yes, it is c2k xk. But anyhow, this 2 is going to be there. Understood how this 2 is involved?
Yes, ma'am.
Okay, because the term is giving us x1 square, x2 square, and rather the terms of degree 2. Therefore, if we differentiate, it will involve with number 2. Therefore, in general, if I differentiate, in general, if we differentiate double summation, j equals to 1 to n, k equals to 1 to n, cjk, xj, xk. Okay, if I differentiate with respect to xj partially, say, what will be a derivative comparing with this? Summation 2 times summation k equals to 1 to n. Yes,
CJK XK.
yes, it is cjk xk. Because if I differentiate with respect to xn, x1, this is c1k. If I differentiate with respect to x2, this is c2k. But in general, if I differentiate with respect to xj, this is cjk. Understood the derivative of both the terms?
Yes, ma'am.
What will happen if I differentiate this third term in the Lagrangian function with respect to xj? Summation is going to be as it is. This middle bracket we have to differentiate with respect to xj, no? And if I differentiate with respect to xj, what will happen? This bracket, if I differentiate with respect to xj, this gives me aij plus, what is the differentiation of qi square minus bi with respect to xj? Is it 0?
Yes, ma'am.
Therefore, this is summation I equals to 1 to m lambda I aij. Correct, na? You can observe from this also. If I differentiate with respect to xj, lambda 1 into, this is ai1 minus lambda 2 into ai2. Right now, therefore, this is going to form summation lambda I aij xj. Okay, no need to explain in detail for this. If I differentiate this last term with respect to xj, what is the value? What is the value? Is it mu j? Rather minus mu j. Because this bracket is going to give me
Yes, ma'am.
minus
Minus
1
much.
after differentiation. Minus 1, na? And minus 1 of minus 1 it is plus 1. Summation will not be there actually, right now? Why summation will not be there? Because here, look at these terms. If I differentiate with respect to xj, remaining derivative is 0. Only the term containing xj will give me the value minus 1. So for minus 1 into minus mu j, it will be plus mu j. Okay, here it will not be a summation. Is the partial derivative clear of all the terms?
Yes, ma'am.
Now, shall I write it?
Yes, ma'am.
Let us come to a partial derivative again. Dou Ly dou xj. First term is giving us cj, right? And the second term differentiation. Half is there already, don't forget half. And this derivative of this double summation is 2 times. Now let me tell you the reason why this half is taken in the objective function just to cancel this 2. 2. For half is already with us. Derivative is 2 times, here I have written 2 times summation k equals to 1 to n Cjk xk. Just to cancel this 2, na, this half was there adjusted. I told you, na, this is the purely an adjustment at the starting of the introduction of the quadratic programming problem. Half is taken just to balance this 2, right? Now let me write the partial derivative with respect to the third term of Lagrangian function. What will be the third term? Minus summation lambda I into this derivative. This term is aij. This is with negative, no? Summation I equals to 1 to m lambda I, and the derivative of the bracketed term is simply aij. Okay, and lastly, may I write minus mu j into minus 1. Minus mu j into minus 1. Everything is equated to 0, right? Therefore, let us just simplify. This is dou L by dou xj equal to Cj plus half and 2 cancels one another. He remains with summation a equals to 1 to n Cjk xk minus summation lambda I aij I equals to 1 to m plus mu j equal to 0. Plus mu j equals to 0. So for the first equation, we were going to write it mu j plus Cj. Mu j plus Cj plus summation a equals to 1 to n Cjk xk minus summation I equals to 1 to m lambda I aij equals to 0, and let me call this as equation number 2. Say what one I will call? One I will call this Lagrangian function. Okay. Now we have completed one job. We have differentiated with respect to original variable xj. Now let me differentiate with respect to the Lagrange's parameters. If we differentiate with respect to Lagrange's parameters lambda I, what will happen? This gives you the ith constant, correct now? Because if I differentiate with respect to lambda 1, first bracket will be there, all the rest will give me 0 value. Therefore, in general, if I differentiate with respect to lambda I, it will give us the ith constraint, the ith original constraint. Okay? Now, differentiate L with respect to lambda I, we get. What we will get differentiating with respect to lambda I? Summation j equals to 1 to n aij xj plus qi square minus bi and equated to 0. Correct now? Is this point understood? Differentiating with respect to lambda 1.
Yes, ma'am.
If I differentiate with respect to lambda 1, it will give us the first constant. If I differentiate with respect to lambda 2, it gives the second constant. Correct now? And all the rest derivatives are 0. In general, if I differentiate with respect to ith Lagrange's multiplier lambda I, this gives us the ith constant. That is what I have written. Okay, this is my equation number 3. Now, if I differentiate with respect to Lagrange's multiplier mu j, say, what it is going to give us? I have to tell you. Differentiating this with respect to mu j. You can look at here. If you differentiate with respect to mu 1, what will be a value? Minus x1 plus r1 square equal to 0, right now? And all the rest derivatives give you derivatives of all mu1, mu2 to mu1, it will be 0. I hope I am very clear to everyone.
Yes, ma'am.
Okay. But in general, if I differentiate with respect to mu j, what will be the value? Is it minus xj plus rj square?
Yes, ma'am.
no doubt with a negative symbol, correct? This gives me minus xj plus rj square is equals to 0. Correct now? Here also it is negative. But negative one can observe. Shall I observe here only? Okay. So this is my next derivative, dou L by dou mu j. Let me observe the negative again in order to write minus xj plus rj square is equals to 0. Therefore, let me call this as equation number 4. Okay. Therefore, the equation number 3 are the original constants. Equation number 4 are the non-negativity restrictions. Yes. Now let us go on differentiating with respect to the remaining variables. Which are the remaining variables now? We have differentiated with respect to x, q and r. Let us differentiate with respect to lambda and mu. If I differentiate with respect to lambda I, what will be a derivative? Let us discuss here. If I differentiate with respect to lambda 1, what is the derivative? Lambda 1 into a bracket. This first is in terms of xj. So if I differentiate xj with respect to lambda, this will be 0. Here the variable is q1. We are differentiating with respect to q1. Therefore, this gives me 2q1 minus, what is the derivative of b1? 0. Therefore, is it lambda 1 into 2q1? If I differentiate with respect to q1 only. I don't know why it is giving you much of the trouble while differentiating partially.
Getting, ma'am.
Everything, no? Can I write
Yes,
directly
ma'am.
now?
Yes, ma'am.
Differentiating partially with respect to qi. Read dou L by dou qi. Yes, this is minus lambda I into, is it 2qi? Check. Minus lambda I into this bracket xj, derivative of xj with respect to qi 0. This gives me 2q minus lambda I into 2q. This derivative is also 0. What the term we were getting? Minus lambda I into 2qi is equals to 0. That one can write dou L by dou qi is equals to lambda I qi is equals to 0. This is the fifth equation. Okay. Then last, differentiating with respect to rj. Let us check what is the derivative with respect to rj. First 3 gives us 0. Last term we have to think of. This is the summation. These are the terms actually. If I differentiate with respect to r1, the remaining bracket gives me 0 value. r2 square, rn square, right? So only first one will exist. This is mu1 into. What will be the derivative of this bracket with respect to r1? Derivative of this bracket with respect to r1. Is it 2r1?
Yes, ma'am.
This is minus q1 into 2r1 if I differentiate with respect to r1. So what will be the value if I differentiate in general with respect to rj? Is it mu j into, right, minus mu j into 2
2
rj equal to 0. If let us just absorb the negative and 2, this gives us mu j rj is equals to 0. Let me write it as equation number 6. So these are the 5 equations we have obtained differentiating L with respect to all the variables partially. Right now? Now what we were going to do, look at this 5 and 6. Now we were going to substitute the value of q, or let me write from 5. Now what this 5 equation implies me, this is lambda I qi is equals to 0. Can I write it as lambda I q I square is equals to 0? Okay. Then let me put this qi square as si, new variable, so that this gives me lambda si equals to 0, where si equal to qi square is a non-negative variable. Okay, therefore the equation number 5 results into lambda I si equals to 0. Now let us check what 6 results into. 6 results into, what is 6? Mu j rj. Mu j rj is equals to 0. Can I write this as mu j rj square is equals to 0? But what is the constant we have? Minus xj plus rj square is equals to 0. Na? Therefore, what is the value of rj square? Is it xj? Therefore, may I write this constant as mu j xj equal to 0. Therefore, equation number 5 takes a new form as say 7 na? And equation 6 takes a new form called as 8. Okay. Now let us observe all the equations we have found with the starting. Equation number 2, is it a linear equation in the variables? Yes, this is a linear equation in variables. Equation number 3, original objective function, linear in this, linear in the variables. Now equation number 4, non-negativity construction and linear in xg. Only the derivative of this Lagrangian function L with respect to the added variables are not linear. Lambda I qi results into lambda si. This is a product of two variables, therefore this is not linear. Similarly, this is also product of two variables. This is not linear. Therefore, except 7 and 8, all the equations are linear. Because this is non-linear equation. This is also a non-linear equation. Therefore, except these, all the previous equations are non-linear. Sorry, all the previous equations are linear equations in the variables. Therefore, these are actually giving us the necessary condition. Rather, those are the Kuhn Tucker conditions, linear Kuhn Tucker conditions, subject to these non-linear. And these non-linear conditions are called as the complementary slackness conditions. These are called as complementary slackness conditions because these are the conditions we have obtained with the help of partial derivatives of the slack variables and which are going to help us in the solution of the quadratic programming problem. For these two conditions 7 and 8 which are resultant from 5 and 6 are called as complementary slackness conditions. Therefore, let me write the Kuhn Tucker conditions again. Thus, Kuhn Tucker conditions obtained are what are the Kuhn Tucker conditions? Partial derivative with respect to xj, we have written mu j plus xj summation equals to 1 to n cjk xk minus summation I equals to 1 to m lambda I aij equal to 0 and this is for j equals to 1 to n.
Ma'am,
Okay.
that is uj mu j plus cj.
Oh, sorry. Yes, it is. Uj plus cj. Good. You're having an attention, please. Okay. This is the first condition. Actually, I cannot call it as first because these are in all n conditions. Resultant of first, right? Correct, na? What is the number of this equation? 5, no? 2, sorry. This
2,
is
ma'am.
2. This is 2 I have written. Okay. Next, if I go for 3, actually 3 is a original objective function. Right now? 3 is original objective function. Sorry. original constant equation. So may I write it? Summation aij xj j equals to 1 to n plus py square minus vi is equals to 0. How many such I we have? 1 to n. What 4 results into? Minus xj plus rj square. How many j we have? 1 to n. Okay. Now 5 and 6 we have taken to be 7, and which 7 results into lambda si equal to 0. 8 gives me mu j xj equal to 0. Again I run from 1 to n, j running from 1 to n. These are my Kuhn Tucker condition, right? Let me just clear what it is. These are my original constraint. What these are? These are my original non-negativity restriction. Okay, and what these two together is called as? These two together are called as complementary slackness condition. Complementary slackness condition. So one important thing to be noted here is that except the final conditions 7 and 8, all the remaining equations are linear in x, lambda and mu. Therefore, we were going to take the three resultant equations supplementary with the conditions 7 and 8. Okay, and these are my Kuhn Tucker conditions. These are the Kuhn Tucker conditions. And next, by using these conditions, mathematician Wolf has given you the algorithm, a systematic algorithm to solve a quadratic programming problem called as Wolf method. Okay. For here, let me just write one important thing to note here is except for final conditions, lambda I si equals to 0, mu j equals to 0, the remaining equations are linear equations in x, lambda, mu and s. Okay. Now the problem becomes equivalent to find a solution of to a set of linear equations which also satisfies these additional conditions. Okay, what is the job now? To solve these linear equations with additional constraints. Additional these two conditions. Just write it. Now the problem has become thus becomes equivalent to finding solution to set up linear equations which also satisfies the additional conditions. X is equals to 0. Okay. Now here, because f of x is strictly convex, necessary conditions become sufficient. Therefore, what is the job remains to us now? Just find a solution to the set of linear equations given by 2, 3, 4 with an addition to 7 and 8. Okay. Then mathematician Wolf has suggested the systematic procedure to find out the solutions of these linear equations. Okay. In the next lecture, we will study what is the Wolf method for solving the quadratic programming problem. If you have any difficulty in today's lecture, you can just ask. Please unmute yourself and you can ask it. Have you understood Kuhn Tucker conditions?
Yes, ma'am.
Good. If you have any difficulty, you can ask. If not, let me stop for today. Okay. You just make the revision of these Kuhn Tucker conditions. And in the next lecture, we will go for Wolf method. Thank you for being with me for this today's lecture.